decades, the West seemed to dominate engineering marvels, but that era is ending. China is launching a breathtaking wave of construction, massive, inventive bridges that rewrite what's possible. How did one country surge far ahead? Instead of just planning, China mobilizes huge teams of engineers and cutting-edge machines to build at scale. These mega bridges are proof. They don't just change skylines, they change how we measure progress. The Danyang-Kunshan Grand Bridge. The number that defines the Danyang-Kunshan Grand Bridge is one that almost doesn't seem real: 164.8 kilometers long. That is a distance you drive between cities, not the length of a single bridge. A high-speed train takes half an hour to cross it. This structure holds the title of the longest bridge on Earth by a margin that is just staggering. Built in just 4 years from 2006 to 2010, this 165-kilometer structure was completed at an average rate of 110 meters per day. But here is the fascinating twist. For much of its journey, this bridge doesn't look like a classic dramatic span over a wide river. It's a viaduct, a continuous elevated ribbon of concrete that carries the Beijing-Shanghai high-speed railway. It sweeps over a flat, waterlogged landscape of endless rice paddies, wide canals, and shallow lakes. From the train window, it might seem like you are just on a slightly raised track. That view is a complete illusion. It hides the epic battle that was won deep beneath the surface. The real enemy for the engineers here wasn't a deep canyon or a windy gorge. It was the ground itself. This entire region sits on soft, spongy, and unstable soil. It shifts, it compresses, and it sinks. Building a normal road on this is difficult enough. Building a high-speed railway, which requires a track as stable and straight as a laser beam, was supposed to be impossible. The ground here could never support that kind of precision. So the solution was to build through the problem. They had to bypass the soft, squishy earth entirely. This is where the true heroes of this project come in: the massive high-capacity piling rigs. Think of these piling rigs as giant mechanical earth-piercing drills. Their job was one of pure, relentless force. They had to drive thousands of concrete pillars called piles deep down through the unstable mud and water. These rigs hammered and drilled these concrete piles down, 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 until each one hit something solid and unyielding, the bedrock far below the surface. Each pile extends 30 to 50 meters deep before reaching bedrock. The scale of this effort is what defines this bridge. This was not dozens or even hundreds of piles. We are talking about tens of thousands of them. A veritable forest of concrete pillars was driven into the ground, one after another, for over 160 kilometers. This was the slow, dirty, and completely invisible work that made the entire project possible. It was a marathon of foundational labor. Once this hidden network of piles was secured, the bridge could finally rise. The concrete pylons and the train deck we see today are just the tip of the iceberg. The real structure, the massive hidden backbone, is that unimaginable grid of concrete roots anchored firmly to the solid earth. This created what is essentially a perfectly stable, perfectly level highway in the sky, completely isolated from the shifting, sinking ground below. The Danyang-Kunshan Bridge is the ultimate lesson in foundations. It teaches us that the most awe-inspiring achievements are often built on invisible, back-breaking work. We see the trains gliding silently at incredible speeds, but the true miracle is hidden from view. A testament to the thousands of piles and the powerful machines that drove them into the earth, creating a colossus that truly defies belief. Jiaxing-Shaoxing Sea Bridge. Now we come to a bridge that faced a different kind of challenge. This was not a fight against unstable ground, but a direct head-on battle with the raw power of water itself. The Jiaxing-Shaoxing Sea Bridge is a 10-kilometer cable-stayed bridge that spans the Qiantang River estuary. But to understand why this bridge is so special, you first have to understand the monster it was built to tame: the Qiantang River tidal bore. This is not a normal river current. This is a wall of water. During the spring tide, a single massive wave of seawater comes roaring in from the ocean, funneled by the shape of the estuary into a towering, churning front that can be over 9 meters high. It moves at the speed of a running horse, with enough force to smash concrete and twist steel. This is one of the most powerful and predictable hydraulic phenomena on Earth. For centuries, it has been a spectacular sight. But for bridge builders, it was a nightmare. The primary challenge was brutally simple. How do you design a foundation that can survive a weekly beating from a wall of water that hits with the force of a freight train? A traditional bridge foundation with multiple legs or a large concrete block would be a death sentence. It would present a huge flat surface for the water to slam into. The force would be immense, a constant brutal shove that would eventually tear the foundation apart or scour the riverbed away from underneath it. The engineers needed a completely new approach. They needed to design a foundation that could not be pushed over. The solution was as elegant as it was ingenious. Instead of fighting the water, they decided to let it flow. They developed an innovative foundation using single, massive piles. Each foundation for the bridge's towers is not a cluster of smaller pillars, but one solitary, gigantic column driving straight down into the riverbed. The scale of these piles is difficult to grasp. Each one is a concrete cylinder with a diameter of 3.8 meters. That is wider than most subway tunnels. And they are driven 111 meters deep into the earth. That's deeper than a 30-story building is tall. This flexible column design is the masterstroke. By using a single circular pile, the engineers presented the smallest possible profile to the oncoming tidal bore. The water does not have a flat surface to punch. Instead, it splits around the smooth, curved surface, flowing past with significantly less resistance. The pile is designed with a degree of flexibility, allowing it to absorb and dissipate the energy of the wave rather than rigidly resisting it. It bends ever so slightly with the force, like a mighty tree swaying in a hurricane, and then returns to its true position. This is the opposite of brute force. It is the application of brilliant, nuanced design to overcome a seemingly unstoppable natural power. The Jiaxing-Shaoxing Sea Bridge stands not because it is stronger than the tidal bore, but because it is smarter. It understands the water's behavior and simply gets out of the way, letting the fury of the river pass by harmlessly. This bridge is a powerful lesson in rethinking first principles. It proves that sometimes the strongest thing you can be is flexible. While other structures might have tried to become an immovable object, this bridge chose to be an unstoppable idea, a testament to the power of clever engineering dancing with one of nature's most awesome displays. Since opening in 2013, the bridge has endured over 500 major tidal bore events without structural damage. The Hangzhou Bay Bridge. This is the Hangzhou Bay Bridge, a 35.7-kilometer cable-stayed giant that does more than just cross water. It conquers one of the most treacherous stretches of ocean on the map. The sheer length of this bridge is enough to boggle the mind. Driving across it feels less like crossing a bridge and more like a short voyage over the open sea. But that vast distance was only the beginning of the problem. Hangzhou Bay is a beast of nature. It is famous for having some of the most powerful and unpredictable tidal forces on the entire planet. The water doesn't just flow in and out. It churns and swirls with incredible energy, making the sea a violent, turbulent mess for much of the year. Then, add the wind. This region is a direct target for typhoons. These are not just storms. They are atmospheric monsters with winds capable of tearing structures apart. So the engineers had to design a bridge that could stand firm against the worst weather the Pacific Ocean could throw at it. But just when you think the challenges couldn't get any more extreme, there was a third hidden danger lurking deep beneath the seafloor. The entire area is peppered with pockets of methane gas. This toxic, highly flammable gas was trapped under pressure in the sediment. Drilling into one of these pockets would be like popping a champagne cork, but with deadly gas erupting into the construction zone, risking explosions and poisoning the workers. The bridge had to navigate a literal minefield underneath it. So how do you build in a place where the water is trying to smash you, the wind is trying to flatten you, and the ground is trying to poison you? You cannot rely on traditional methods. You need to become a master of assembly, building huge pieces on land and then performing a carefully choreographed dance at sea. This is where the true heroes of this project come in, the massive, specialized cable-laying ships. These are not ordinary boats. These are floating industrial platforms, some equipped with cranes capable of lifting 3,000 tons. That is the weight of a small warship. Think about the segments that make up the bridge deck, the giant concrete and steel girders. Each one is a colossal piece of engineering itself. These segments were constructed in safe, controlled factories on dry land. This ensured perfect quality and kept workers out of the dangerous bay for most of the construction process. Once these mega-pieces were ready, the cable-laying ships moved in. Their job was a high-stakes ballet in the middle of the ocean. These ships had to transport the gigantic prefabricated segments from the shore out to the open water. Then, in the midst of swirling tides and howling winds, they had to hold their position with pinpoint accuracy. The cranes would then lift these massive segments, each one weighing hundreds of tons, and place them into their exact position high above the water, connecting them to the towers with the stay cables. It was a process of incredible precision performed in the most imprecise and chaotic environment possible. Each successful placement was a small victory against the elements. The bridge required about 500 of these massive prefabricated segments. The bridge quite literally grew, piece by mammoth piece, assembled from the sky down by these floating titans of industry. Sky Bridge at the Hong Kong International Airport. This is the Sky Bridge at the Hong Kong International Airport. Now, calling this a bridge almost doesn't do it justice. It's the world's longest airside passenger bridge, stretching 200 meters between Terminal 1 and the satellite concourse. But its length isn't even the coolest part. Imagine walking across a bridge with a glass floor high above the tarmac with giant passenger jets taxiing right underneath your feet. But for the engineers, this beautiful bridge presented an unbelievable nightmare of a problem. How do you build and install a 5,100-ton, 200-meter-long monster right in the middle of one of the busiest and most efficient airports on the planet? You can't just shut down a huge section of the airport for months. Every hour of downtime costs a fortune and disrupts thousands of travelers. The solution to this impossible puzzle wasn't just strong, it was smart. It was all about precision. This is where the real magic happens, and it involves a company called Mamouet and some of the most incredible machines ever built. The strategy was as bold as the bridge itself. Build the entire thing off to the side and then, in one single, perfectly choreographed move, slide it into place. This is called accelerated bridge construction, or ABC, and it takes a massive construction project and turns it into a single surgical operation. The stars of this show were two pieces of equipment: the self-propelled modular transporters, or SPMTs, and the MegaJack 5200 system. The SPMTs look like a mechanical centipede. Imagine a fleet of multi-wheeled platforms, each with its own computer and power system, all able to link together and move as one. These platforms were lined up underneath the fully assembled bridge. This wasn't a lightweight piece of steel. We're talking about a structure that weighed as much as a large cargo ship. The SPMTs lifted the entire 5,100-ton weight and began a slow, incredible journey. They had to carry this behemoth 3.5 kilometers across the live airport. That's a journey across active taxiways, following a carefully planned path. It was a slow, nerve-wracking parade of epic proportions. Once they reached the final location, the next challenge began. How do you lift this colossal weight up and over the existing structures to its final resting place, over 14 meters in the air? You don't use cranes. In such a tight, confined space, that's too risky. This is where the MegaJack 5200 system came in. Think of this as the most precise and powerful set of jacks you can imagine. These jacks were positioned on the permanent support pillars. The SPMTs, with the bridge still on their backs, moved perfectly into position underneath these jacks. Then, in a perfectly synchronized ballet, the megajacks lowered down, connected to the bridge, and took the immense weight from the SPMTs. Then, with millimeter precision, the jacks began to lift. Slowly, steadily, this entire sky bridge was raised into the air. The SPMTs could then simply drive away, and the jacks gently lowered the bridge exactly onto its permanent supports. The entire installation, from the start of the move to the final lower, was completed in a breathtakingly short window. What could have taken months of disruptive, noisy work was done in one go. This is the new face of mega engineering. The installation took 55 hours, work that would typically require 4 to 6 months and significant airport closures. The Shihuman Bridge. Now we come to a bridge that represents a different kind of ambition. This is not about crossing a great distance over land or battling toxic gas. This is about pure vertical height over deep, open water. We're talking about the Shihuman Bridge, and it belongs to an elite class of engineering, the long-span suspension bridge. Its main span stretches an astonishing 1,650 meters across a strait. Completed in 2009, this was China's longest suspension bridge span at the time. That is over a mile of nothing but air between the two main towers. To understand the scale, that is long enough for 5 of the world's largest aircraft carriers to be lined up end-to-end with room to spare. This bridge does not just cross the water, it soars over it, a permanent fixture in the sky. But building a bridge of this type over a deep channel presents a unique set of problems. You cannot build scaffolding from the bottom up. The water is too deep and the shipping lanes are too busy. So the entire construction process had to happen from the top down, starting with the most critical element of any suspension bridge, the main cables. These are not just big ropes. These 2 cables are the literal lifelines of the entire structure. Each one is a massive bundle of high-strength steel wires, thick and incredibly strong. They are what hold up the entire weight of the bridge deck. And the process of creating these cables in mid-air is one of the most breathtaking sights in all of engineering. It all starts with the catwalk spinning system. Before the main cables can be built, the engineers first construct a temporary pathway. This is the catwalk, a narrow, precarious-looking web of wire and mesh that hangs between the 2 towering pylons. It looks like something a spider would build, a fragile thread swaying in the wind high above the water. But this delicate-looking web is deceptively strong. It is the construction highway for the bridge's backbone. Once the catwalks are in place, a special spinning wheel called a traveler moves back and forth along them. This wheel does not carry a full, thick cable. That would be far too heavy to lift all at once. Instead, it carries a single, continuous loop of steel wire. This wire loops from one anchor point on one side of the bridge, all the way across to the other side and back again. The traveler goes back and forth thousands of times, each trip adding 2 more wires to the growing bundle. Slowly, painstakingly, this back-and-forth process builds up the massive cable, one single wire at a time. It is a marathon of precision, creating a cable composed of tens of thousands of individual wires, all bound together to form a single immense strength member capable of supporting thousands of tons. With the 2 main cables finally hanging in their permanent curve, the next challenge begins: lifting the bridge deck. This is where the deck erection gantries come in. These are specialized traveling cranes that literally ride on the very cables they are helping to load. They look like mechanical insects crawling along the main cables. Their job is to lift the pre-built sections of the steel deck from barges on the water far below. These deck sections are enormous, each one a heavy, wide piece of the roadway. The gantry crane locks onto a section, carefully lifts it from the barge, and then carries it into its precise position high in the air. Workers then connect it to vertical suspender ropes that hang from the main cables. This process repeats section by section, starting from the 2 towers and moving outward towards the middle of the span. It is a slow, deliberate dance in the sky, with the final piece being slotted into the very center. The entire roadway, the part we drive on, is literally hung from the sky, assembled piece by piece without any support from below. The Shihuman Bridge is a masterclass in defying gravity. It demonstrates that by breaking down a monumental task into thousands of small, precise steps, we can build structures that seem to float effortlessly over impossible gaps. It stands as a powerful reminder that the most solid and permanent things can sometimes be built from the top down, a testament to the power of suspension and the engineers who master it. This bridge demonstrated that Chinese engineers had mastered suspension bridge construction at world record scale, a technology previously dominated by Japan, the United States, and Europe. The Guizhou Bridge. The Guizhou Bridge does something that traditional engineering said was impossible. Its 2.68-kilometer cable-stayed section is held up by 6 towers in a row, a configuration that creates a nightmare of competing forces between the pylons. Its main section stretches for 2.68 kilometers, and it is supported not by the usual 2 towers, but by a line of 6 identical pylons rising from the water. This multi-pylon approach seems like a simple idea. Why not just use more towers to cover a long distance? It makes sense intuitively. But in the world of cable-stayed bridges, this is a radical departure from the norm. The classic 2-tower design is simple and stable. All the cables pull back towards 2 massive anchor points. The forces are direct and easy to manage. Now, picture 6 towers in a row. If you just string cables from each one to the deck, you create a much more complex puzzle. The deck is no longer being supported from just 2 points, it's being held up by 6. The tension in the cables from one pylon affects the tension in the cables of its neighbors. It becomes a delicate ecosystem of force. If the balance is off, one pylon could be pulling too much weight, straining the entire system and pulling the deck out of its perfect level alignment. The primary challenge was achieving harmony across this entire structure, ensuring that all 6 pylons work together as a single unified system. The solution to this puzzle was not found in a bigger crane or a stronger steel. The solution was found in control and information. The entire bridge was built using a method called balanced cantilever construction, and the magic was in the equipment that made this method so precise. Here is how it works. Instead of building the deck from one end to the other, the construction begins simultaneously at each of the 6 pylons. Think of it as building 6 separate smaller bridges that all have to meet in the middle perfectly. At each pylon, a specialized construction platform is set up. The process starts by attaching a pre-built deck segment directly to the pylon. Then, using a massive computer-controlled hydraulic jack, the next segment is lifted into place on one side. Then, to keep everything balanced, an identical segment is immediately lifted into place on the exact opposite side. This is the balanced part of a balanced cantilever. It is like a seesaw, with the pylon as the fulcrum. By adding equal weight to both sides at the same time, the pylon remains perfectly centered, and the forces stay in equilibrium. The deck gradually extends out from the pylon in both directions, arm-like, with each new segment being carefully locked into place. But with 6 pylons doing this dance at the same time, how do you ensure that when these long arms finally reach out to touch each other, they meet perfectly? A miscalculation of just a few millimeters at one pylon could compound into a gap of centimeters where the segments are supposed to connect. This is where the second piece of technological brilliance comes in: the real-time, synchronized stress monitoring system. This bridge was essentially built with a nervous system. An intricate network of sensors was embedded in the concrete, attached to the steel and fixed to the cables. These sensors constantly measured the slightest strain, the most minute shifts in stress, and the precise position of every critical component. This data flowed back to a central command center, giving engineers a live digital readout of the bridge's health and alignment during every single second of construction. The synchronized hydraulic jacks were guided by this data. If the sensors detected that one side of a cantilever was developing more stress than the other, the jacks could make microscopic adjustments. If the monitoring system showed that one pylon was beginning to carry a disproportionate share of the load, engineers could adjust the tension in the cables elsewhere to compensate. This was not construction by brute force, it was construction by surgical calibration. The Guizhou Bridge was not just built, it was grown, with its development carefully guided by a constant stream of information. When the final segments were lifted into place at the very center of each span, they fit perfectly. The alignment was flawless because the entire process had been managed with the precision of a symphony conductor, ensuring that all 6 pylons and their growing cantilevers played in perfect harmony. The Lingdingyang Bridge. Now, let's step away from the bridges we can see and drive across today. Let's venture into the near future, to a project that is currently a set of blueprints and digital models, but one that represents the absolute cutting edge of what bridge engineering can be. This is the Lingdingyang Bridge, part of the Shenzhen-Zhongshan link. Currently under construction and nearing completion, it is designed to be a true leviathan, stretching an almost unbelievable 47 kilometers across the sea. The sheer length is enough to place it in a league of its own. But the real genius and the real challenge is not just in covering that distance. It is in what the bridge will carry. This will not be just a road, it will not be just a railway, it will be both. A fully integrated double-decker Titan designed to carry a constant flow of highway traffic and high-speed trains, all at the same time, linking the massive economic hubs of Shenzhen and Zhuhai. The bridge will reduce travel time between the cities from over 2 hours to approximately 30 minutes. Merging these two types of transport into one structure over such a vast open sea is a problem of incredible complexity. Think about the forces at play. A highway is a chaotic, dynamic load. You have thousands of cars and trucks, each one braking, accelerating, and changing lanes. The weight is constantly shifting and moving in unpredictable patterns. Now, contrast that with a railway, especially a high-speed line. A train is a massively concentrated, incredibly heavy load that moves at tremendous speed on a perfectly fixed path. It requires a track that is rigid, stable, and flawless. The bridge must be stiff enough to not bend too much under the train, yet it must also have the flexibility to handle the constant, varying pressure from the road. Designing a structure that can do both for 47 kilometers, while battling ocean winds and tides, is a task that would have been unthinkable just a few decades ago. So, how do you solve a puzzle this immense before a single shovel hits the dirt? The answer lies in the most crucial piece of equipment for this project, and you cannot even touch it. It is not a crane or a jack, it is software. The entire project is being born and perfected inside a computer using a process called Integrated Building Information Modeling, or BIM. Think of BIM as a perfect digital clone of the entire bridge. It is far more than a simple drawing. It is a living, breathing model that contains every single detail. Every beam, every cable, every bolt, every electrical wire is represented. But the real magic is that this digital twin is smart. Engineers can subject it to a lifetime of simulated stress in a matter of days. They can run a virtual high-speed train across the lower deck while simulating a traffic jam on the upper deck during a Category 5 typhoon. The software will show exactly how the forces interact, where the stresses are too high, and how the materials will behave over decades. They can test 1,000 different design variations, 1,000 different material choices, all with the click of a button. This process identifies conflicts and weaknesses long before they could become catastrophic, expensive problems on the actual construction site. This digital rehearsal is what makes the Lingdingyang Bridge possible. It is the ultimate tool for managing complexity, ensuring that the road and rail components will work in perfect safe harmony for their entire service life. This bridge represents the new frontier of engineering, where the most important construction doesn't happen with steel and concrete, but with data and algorithms. It is a testament to a new kind of power. The power to build flawlessly in the digital world first, so that the physical world that follows is nothing short of a masterpiece. When completed, this bridge will stand as proof that the most ambitious infrastructure engineering on Earth is no longer happening in the West. It's being designed and built in China, at a scale and speed unmatched anywhere else.